Hi all. Today we give some brief introduction to Galerkin projections method, which is a fundamental to many numerical discretization techniques for solving partial differential equations like finite element method, spectral element method, and spectral methods. And this numerical discretization method that I mentioned now have some many geometrical flexibility and also incorporate higher order approximations in a very efficient manner in comparison to a structured finite difference or higher order finite difference method. But in this video, I will not go very deep inside about the fundamentals of finite element methods, but that will be given in a later set of videos based on this beautifully written book called Finite Element Method Analysis by P. Sheshu. That I'll come during the end of this video. I'll give you some brief introductions about this book. Now, so what this material says about that. So let us assume that we have a Poisson equations defined by equation 1 with the homogeneous Dirichlet boundary conditions, and for in a one dimensional case it ends up with this equations 2 in a bounded domain with plus or minus 1, and you had represent the exact solutions and you represent the numerical solutions, and we try to approximate these solutions for this differential equation in a finite dimensional space x0 here, and it is spanned by n basis function phi 1 to phi n, satisfying those homogeneous boundary conditions. And we define a test function called v, and it's an integrable functions, and we seek solutions which can be expanded in this finite dimensional space using these coefficients of expansions. And using these formulations, integral formulations, this equation 1 can be written in a in this fashion, like weighted residual fashions, which are in a weak integral formulation or weak formulations. And the aim is to solve these equations by these formulations. Directly it gives you n equations for n unknown coefficients, and we also take this v to be these basis functions in that finite dimensional space. So based on these conditions, we can also define a residual call, making this to the left hand side and this to be as a residual functions. And we also with this setup, it make it is it brings up the concept that this residual will be an orthogonal to the n-dimensional space. So based on this, that's what the name formulation called weighted residual techniques. So if it is an orthogonal function, it means that the inner product of between that function, the test function, and that residual will be a zero. And once we are increasing the span of the basis functions, that n is increasing, then the u will be converging to the true solutions. And based on these things, and also using some vector calculus theorem like divergence theorem and gradients theorem, and using integration by parts, we can relax the constraint on the trial functions to be single integrable functions. And using those divergence and gradient theorem, we can end up with formulations from equation 1 to equation 3 to equation 5. So we also assume earlier that bound this v vanishes at the boundary, so this second term will get vanished, and now we will be ending up this equation 3 here using that integration theorems. We will be ending up with the equation 6, which is single integrable functions. So now here comes the question. So what kind of basis functions we wanted to utilize in this weighted residual or weak formulations? What makes a different kind of method like finite element method, spectral element method, and spectral element? There are many choices of the basis functions that we will briefly will just detail in this one. So once those basis functions are substituted here, and we will get some kind of matrix equations. On solving these matrix equations will give you this coefficient of expansions, and we already know explicitly the basis function. Then that will give you two solutions, and increasing the number of basis functions will increase the accuracy of this approximate solution. It will give converge to the two solutions. And also the conditioning of this matrix anywhere depends upon the what basis functions we are choosing one, and it would be better that if the basis functions are orthogonal and they are not linearly dependent, and more far from linearly dependent, and span the basis widely. It not only this formulation can be applied, initial residual formulation can be applied for only for the Poisson equation. It can also apply for convection diffusion equations. This is a convection operator. I'm substituting that, we'll get this formulation, equation 14, and this will be like kind of some called that matrices like stiffness matrix, and that will be coming, what kind of terminology will be using in the finite element analysis. So here I needed to emphasize you, if you could see the previous video that I emphasized that uh, I emphasize in this video that I have put almost like 3 minutes, that we use many function approximations for in numerical simulations for solving partial differential equation. Also, we use function approximations for machine learning tasks, like given a training data and try to fit input output functions, and what type of basis functions and the and the discretization scheme differs. Here, the polynomial basis functions is usually for the finite element method. So let us come back to this uh, the script. So this basis functions can be of two main forms. One is a nodal basis, and is another one is model basis. Nodal basis in sense that when we solve for the coefficient expansions, usually this coefficient will give you the true solutions at the respective nodal points. Model basis will be seeing after this one. So what are the kind of nodal basis functions? There are many basis functions. So one is like Lagrange polynomials, and we will not go through much about what is Lagrange polynomial. That we will see possibly in a later video. Well, this is going to be just a brief introduction about what is Galerkin method, and what is a weighted residual method, what is weak formulation, what is integral formulations, what is orthogonality between the test function and the residual, how do the coefficients of expansions are computed, and what kind of basis functions are we are choosing. So those are the fundamental ideas behind this video, not going that in depth into the kind of characteristic of the basis functions, like defining what is legendary polynomials, all those stuff. So and there again I can say that basis function can be of a global basis function, which will have some continuity throughout the domain, or the local basis which have only a local support. So finite element method is mostly based upon the local basis functions, which is defined as something like that, which it will interpolate between this nodal between x1 to x3, and it will be vanished outside of this domain. And if you go for a higher order polynomial, it will be extended from x1 to x4, which we will be covering more detail about what type of basis functions, what is linear basis functions, local support linear basis functions, and quadratic basis functions, all those kind of basis functions, and how to construct those matrix equations through these basis functions, all will cover through based on the book that I mentioned earlier. So the model basis function is not some kind of a local support. It's not like kind of vanish outside that conditions. It has a nice property like orthogonality property that will be utilized to make a structured matrix. And like legendary like spectral element methods, all those things are based upon this model basis function, which we will not cover detail in this one, possibly in some other videos. So this is the overall idea about this Galerkin projection method. And this Galerkin projection method is a very powerful method to solve those partial differential equations, like I mentioned in the beginning of the tutorial. and it ends up with these equations from equations. This is integral formulations of weighted residual formulations from the equation one that is defined in our Poisson equations. But how those things, a more elegant way of introducing this finite element based on these Galerkin projections, and what are the applications, and how to choose the elements, how to discretize the domain, how to form the weighted residual all those things will be covered in this based on this book, maybe in like planning for 4 to 5 videos, or maybe 3 to 4 videos will be sufficient enough to cover this first three chapter. I'm not that much interested to go beyond this three chapters, but these three chapters will give you a more fundamental reason behind this final element method to be successful to apply for the structural mechanics applications. So what is meant by a finite element, and what are the weighted residual method, and what is the single trial functions, and what is general weighted residual method, what is variational formulations, and how to go for a single trial function into a piecewise linear bunch of trial functions. That similar that bunch of trial functions will be going to the concept of the that expansion that I mentioned earlier related to this one, these equations, that we will cover on this based on this book. So I'll just quickly glancely go through these 100 pages for your knowledge. So it starts with the necessity for this simulation techniques, and where does this finite element method stands. What are the key characteristic of this finite element method? It has assuming that numerical solution based on assumed trial solution, a single trial solution, then the residual is formed. Because this trial solution is not exact solution, then it will not satisfy the equation. The residual is formulated, but that residual is not necessary to be pointwise. It has to be overall covering the whole domain. So that will be an integral formulations, that weighted residual formulation, either residual integral formulations, and those domains are discretized into finite elements to make the trial functions to be local support, and that will it can be also called as element level shape functions. So these are the overall idea they give you briefly in the opening chapters. They are neatly and very structurally written for beginners to understand, and how this diffusion equation is not necessary to be related to structural mechanics, also related to the heat diffusion equations with the heat source, and also some applications which we will more focus about the fundamental behind this finite element method. And once you understand finite element method, then we will give the motivation is can be understood. So these are some of the applications in aerospace, in automobile, and in everywhere wherever yeah, structural engineering and fluid mechanics and thermodynamics are utilized. So this final element of becomes a very essential method to solve those governing laws. So here it starts with the weighted residual formulations. How those differential equations are end up in a weighted residual formulations, and how the single trial function is utilized, and that if we are using a single trial functions, we can have a single it can be a linear or quadratic or higher order polynomials based on the requirement and based on the conditions of the boundary conditions. So how the single trial function with the small coefficients becoming a problematic and doesn't gives you a minimal residual throughout the domain is being explained in this problem, and the necessity for us to formulate more basis functions, local support basis functions, and weight integral formulation is motivated based on the above example. So we will similar to that previous that lecture, we will be for why what is the necessity formulate this is be given motivated by those above examples, and we form this integral residual method. and we'll for every test functions will be based on that coefficient expansion basis functions, and we'll have n basis function. We'll have we formulate n equations for based on the n basis functions, and that n coefficients will be formulated, and that n coefficients will be simultaneously solved using a matrix equations. So that will give you a better minimized residual compared to using a triangle trial functions. So this is being motivated again with this heat diffusion equations. Again, this weighted residual method can go for a weak formulations. From this weighted residual method, how the weak formulation is formulated for different governing problems like structural mechanics. It's very well written, but we will go deeply into all these facts, and it's very neatly written. And this is what the section says, that how the variational formulation of through this weighted residual method is formulated. These variation formulations is the basic ideas behind that. I introduced earlier about this variation of formulations, like how the second order differentiations being relaxed to make using the integration theorems to make the formulation similar to this one. That's the same thing that is being introduced to the previous script here. And this equation 3 is formulated through this integration by parts into these formulations. The equation 6, same thing they are introducing here. And from this how do we going into the concept of finite element, weak formulations to finite element, been covered in the rest of this second chapter. So once this is been covered and this fundamental is nicely introduced, possibly I will give you an every emphasis on every portion of this, especially the second chapter is a very fundamental for everyone who ever wanted to go and study finite element has to understand this very basics of how these equations, how this element stiffness matrix, how the global matrix are formulated is a very key understanding. It's not that you're taking a package and clicking the button and trying to get a solution. No, not necessary that it won't give you a good engineering perspective. So you have to understand the governing laws and how those governing laws have ended up in partial differential equations, how those partial differential equations have some complications based on complex boundaries and complex boundary conditions, and what motivates to define this finite element instead of finite difference method, and what is the speciality of this finite element method, and how is this speciality of finite element in making these elements, especially to the higher dimensional, two-dimensional, three-dimensional unstructured domain, will be covered using based on this book. That is for now. Hopefully, we'll see in future tutorials covering these topics in a detailed way. Thank you.